Distance-time graphs, such as the one being examined here, provide a clear and visual way to understand how far an object has traveled over a given time period. These graphs are particularly useful because they enable us to break down and analyze the entire journey of an object. For example, this specific graph could represent the path taken by a cyclist. It tells us that the cyclist has traveled a total distance of 50 meters in a span of 11 seconds. However, what makes these graphs even more informative is their ability to reveal detailed insights into the different stages of motion throughout the journey. Interpreting each segment of the graph is an essential skill. The most fundamental concept to grasp is that the gradient, or slope, of the line at any specific point on the graph directly indicates the speed at which the object is moving at that moment. This relationship exists because gradient is defined as the change in distance divided by the change in time, which, as we know, is precisely the formula used to calculate speed. Therefore, it is important to remember that whenever you are reading a distance-time graph, the gradient will always tell you the speed of the object. Let's look at the first section of the graph where the cyclist travels a distance of 20 meters in just 2 seconds. In this case, the gradient would be 20 divided by 2, resulting in a speed of 10 meters per second. Since the line is straight, we know that the speed is constant throughout that segment. The consistency of the line's slope confirms that the cyclist maintained the same speed without speeding up or slowing down. In contrast, when we observe a flat, horizontal line in the middle of the graph, it tells us something very different. A flat line means that the object is stationary because the gradient and therefore the speed are both zero. This indicates that there is no movement taking place during this time period. Now, if the line starts to get steeper as it progresses, it means that the gradient is increasing, and since gradient corresponds to speed, this part of the graph represents acceleration, which is an increase in speed. On the other hand, if the line becomes less steep or the gradient decreases, it indicates deceleration, meaning the object is slowing down. One particularly important detail to note is that when the speed of the object is continuously changing, as it does in the curved sections towards the end of the graph, determining the speed at any specific moment becomes a bit more challenging. Unlike straight segments, where we can calculate speed by simply dividing total distance by total time, curves require a different approach. If we want to know the speed at exactly 8 seconds, we must draw a tangent to the curve at that specific point. A tangent is a straight line that just touches the curve at one point and has the exact same slope as the curve at that location. To determine the speed from the tangent, we select 2 points on the tangent line and use them to find the change in distance and the change in time. For example, if the change in distance between these 2 points is approximately 12 meters and the change in time is 3 seconds, we divide 12 by 3 to get a speed of 4 meters per second. In summary, this video has explained how to interpret distance-time graphs. Straight lines indicate that the object is moving at a constant speed. Flat horizontal lines show that the object is not moving and is stationary. Curved lines represent periods of changing speed. To calculate the speed at a specific moment in time, you need to determine the gradient of the graph at that point. If the point lies on a straight line, simply calculate the gradient of that line by dividing the change in distance by the change in time. However, if the point lies on a curve, draw a tangent at that point and then calculate the gradient of the tangent line. That brings us to the end of this explanation. If you found the content helpful, feel free to give us a like and subscribe, and we look forward to seeing you in the next video.